ways you'll see data displayed from a GCMS experiment. The first is a chromatogram, in this case a total ion current, and the second is going to be a mass spectrum. So note that this is technically referred to as a chromatogram. I have a tendency to slip up and say chromatograph, but the chromatograph is the instrument, the chromatogram is what it gives you. And what it gives you here is total ion current, and so this is telling you the total ions that were coming out at each point in time as they traveled through the gas chromatography part. And then down here, we're looking at the individual ions at that point in time. So each point in time on the chromatogram will have a corresponding mass spectrum. And on the mass spectrum, here our x-axis is m/z, so our mass to charge ratio. Whereas on our chromatogram, the x-axis was time. The peaks in the chromatogram are representing, ideally at least, individual compounds, and so the compounds are getting separated through the gas chromatography step, both by their boiling points as well as by their interactions with the column. As they come off of the column, well, now they go to an ionization source. In this case, we have an electron impact ionizer, and so what it does is it shoots electrons at the compounds as they come off, and it knocks electrons off of those compounds. Electrons are negatively charged, so when you lose an electron, you become positively charged. The positively charged ions are then directed to a detector. We have a quadrupole detector, so it uses magnets to send those ions traveling to the detector. And they will travel at a speed that is dependent on their mass to charge ratio, this m/z. In this way, you're able to take the ions, even though they came out of the column at the exact same time, and now you're able to separate them and be able to measure their mass to charge. And so what are we seeing? If you were to say, pick one point in time, so like one peak, you would see something down here. And if you were to choose a different point, you would see a different thing and a different thing and a different thing. And what this is saying is at this exact time point, this is the sum. This is the sum of all of this. So if you think about, okay, well, if I look at this peak, this that I'm seeing here is if I were to add all of these peaks together. And all of these peaks, well, here what you're looking at are individual ions. And so you can have the parent ion, which is basically the form where it just has an electron popped off, but it's still, the mass is the same. And so if it has just a charge of, you lose an electron, you get a +1 charge, and so your m/z would be your molar mass, or the average mass. And so it's the mass, not the molecular weight, because of the isotope differences. And so also because of the isotope differences, then you have these kind of little peaks on the side of the bigger peaks because of differences in abundance of, say, carbon-12 and carbon-13. Each of these is then also going to have fragment ions. So this was an electron impact ionization, and so basically you shoot electrons at the compounds as they come off of the gas chromatography. You shoot electrons at them, and that kicks off electrons, and so that's how you get the positive charge. But it's also harsh, and it can break the molecules. And so I don't know about you, but I might get a broken bone if I had a bunch of stuff being thrown at me. And so when you throw electrons at compounds, then they can fragment, and so then you get these fragments. So you get this complicated looking spectra. The complication is both good and bad. The good is that it gives us more information to ID it, kind of like a fingerprint. The bad is that then it gets all messy. Thankfully, there are huge databases of collected data for compounds, for mass spec compounds. And what you can do is, if you actually double click on something, you can see it searching the library, and it's finding that this is a good hit to malate. So malic acid, more specifically, it is the bis trimethylsilyl ester, so the 2-TMS malate. And here what it's also showing is the differences. So if I just do this, it doesn't show me that. But here, if I show the differences, basically now it's saying, okay, we've got this much stuff that we shouldn't have, and we have this much stuff that we should have. But if you look and see, these numbers are a lot smaller than the numbers that we actually got for our peaks. You can also then, if you wanted to, you could go to the text, and you could get the information if you wanted the compound name. You can also then come over here, and if you go to spectrum tabulate and you go to search, then you can see an even longer list. And if you go to spectral data, you get the abundance for each of the MZ ratios. And so you can copy this, and if you say the software couldn't identify it, you can then go search in a database that could. And so there's some good tools online, and you can also predict the spectra that you would expect for a compound that isn't in the database using tools like GCMS ID. Various tools, GOLM is good for if you're trying to identify a compound, lots of cool stuff. But anyway, that's how you can get the data from the spectra. And remember, the spectra is coming from a specific point in time after compounds have basically come off or eluted from the gas chromatography part. And so here the separation is coming based on differences in boiling points as well as differences in interactions with the column. And that's how you get the separation of the compounds. Once they get separated, then they get ionized, and the ionization also fragments them sometimes. So then those ions, those charged particles, are now directed to a detector with magnets. So look, we use a quadrupole, so there are different forms of mass spec detectors and stuff. We have a quadrupole, so it has basically magnets that direct those charged particles to a detector. And then it's able to basically travel differently depending on their mass to charge ratio. And so that's how you can then separate the ions. So you can see, say, the paired ions and then the fragment ions. And then you can compare those to databases of known ions, of known compounds, in order to see whether what yours might be a good match to. There's often going to be a lot of different potentials, and there's a lot of molecules that have similar fragmentation patterns. They have similar M/Z, all of these various things, and they might, hopefully though, they won't travel the same on the gas chromatography part. So you kind of take advantage of the fact that the gas chromatography, not only does it separate these so that we don't have the spectra overlapping as much. So if you look on either, so as you go through a peak, you'll see that in a really small amount of time, the signal kind of changes a little, the abundance of each of the different peaks, and that's because there's not as much other stuff coming out, or there's new other stuff coming out. Because remember, what we're seeing up here is kind of what we're seeing is the sum of all the things that were coming out at that point. And then here you're looking at that specific point, but you're still seeing the fragments of everything that was coming out at that point. And so if you have a bunch of things, they're going to have overlapping peaks, and then it's going to make it hard to identify what was actually there. So separating them further is going to make this better. And you can do that by changing the temperature gradient, making a longer ramp, things like this, to better separate based on differences in their boiling points. If they have similar boiling points, what you can do is you can try using a column that will interact more with one of them than the other. So there are various strategies to improve the resolution that you get with the gas chromatography. And then it's off to the detector. One of the things that you want to do too is to help really be sure about what an idea of a compound, as well as to maybe even quantify the compound, is to run standards. Say I knew I was interested in looking for malate. So these were bacterial extracts, and there was a lot of stuff in there. And I said, okay, what were some of the key things we're interested in? Well, one was malate. And so what I did was I ran a standard of malate. And so you can see that this is where malate ran. And in fact, what I could do too is if I were to go back to my sample before, so if I go back to that sample that we were looking at before, what I can do here is I could do a couple things. One of the things is I could have gone to Chromatograms, and I could have gone to extract ion chromatograms, and I could have put in the M/Z I expected and had it predict that, and then only show me the or have it use that and then only show me the M/Z for that. And then you would probably see that there were different time points at which there were things with that same M/Z. So that would be for the parent. But what I can also do is, since I have a standard of malate, what I can do is I can actually overlay these. And so if I were to overlay these, what I could do is if I stick on the malate, now I can see them both together and overlaid. And you can see that they're actually right on top of one another. And so awesome. I can also, if I want to unmerge the view, I can do that. And you can see that both of these are eluting at the same time, and they have the same signal. And so that is a good positive ID of malate. If I wanted to, I could do a dilution series of the standard of malate and then try to quantify how much was in my sample. But for now, I'm happy just knowing it's malate. If you don't have standards of the compound you know, what you can also do is you can calculate a retention index. If you take a series of standards of just known carbon lengths and you measure how long it takes them to come out, and then you can kind of compare between, like, what it came out between carbon 10 and carbon 12 or something like this. And then there's actually like a formula where you can calculate retention indices, and you can find these in databases. So lots of cool stuff. So remember that these are the chromatograms, and this is the mass spectra. The chromatograms, each of the peaks represents a compound, and the spectra, each of the peaks represents an ion. And so the combined information is really helpful for trying to identify compounds.